Okay, so let's see what we can do today. So I will pick up from where I left yesterday, and I also want to say something to, yeah. So today is the third day. So yeah, so so we have seen the definition of so recall that whenever I have f to be mapped from x to the n to c, then we gave this definition of an automorphic form as just let me see. Yeah, so it was like something like f of I wanted to recall that something else here, that slashing action, which I wanted to define here. Yeah, so these are the notations which I used. So f of mz equals to n of cz plus d to the power of k times f of z. And then in the background, there is a discrete subgroup. And this is for all m inside gamma. And the second was that f is regular at the cusps. Okay, and then when I have this gamma, so this is, and if I have gamma to be of finite index inside SL2Z, SL2 of OK, SL2 of OK for K totally real, then we call F to be Hilbert modular form. Okay, then F called Hilbert modular form. Okay, and then we also saw that weight zero Hilbert modular forms are weight zero Hilbert modular forms are constants. Okay, so Hilbert modular forms of weight zero. Okay, so this is zero everywhere. Nothing but they are constants. Okay, and then we also gave example of Eisenstein series. So this was defined by E to K was defined by summation 1. Okay, so there is this 2K weight here and then applied to M. Yeah, and then M belongs to gamma mod gamma infinity like this. So these were the things, and then today we are going to see. Yeah. So what we saw yesterday was that Hilbert modular forms of weight zero are constants, and so today we'll see the first thing we'll see today is something which is known as the Gutsky-Queeker principle. Okay, and then to do that, we first look at the effect of the multipliers. Okay, on the Fourier coefficients. Okay, so this is regarding the effect of multipliers. So this is multipliers on Fourier coefficients. Okay, so let's look at this. So suppose I have f of z equals to say summation a g, okay, e to the power of 2 pi I s of gz, like this. Okay, and then here g belongs to the translations which come from gamma. So I'm not writing the gamma here, but this, and then it is of weight say k1, k2, and so on to kn. Okay, and let's take a multiplier inside lambda. So I have epsilon, which is inside lambda. Okay, and so that, yeah, so once I have an epsilon inside lambda, I know that there is a b such that I will have epsilon b 0 epsilon inverse. Okay, so things like that will be inside inside gamma. Okay, then I will have, if I look at that epsilon, then I will have, yeah, so then I can look at f of epsilon z plus b. Yeah, so then this will turn out to be epsilon 1 to the power of minus k1, and then epsilon n to the power of minus kn, and then I'll get here f of z. Yeah, so this one we can also write this as n of epsilon to the power of minus k f of z. Just a notation. Okay, then what do we see from here? So from here we see that my a of g epsilon, okay, the Fourier coefficient for g times epsilon will be equal to the Fourier coefficient for ag times e to the power of 2 pi I s of gb, the trace of gb, times this n of epsilon to the power of k here. Okay, this is the result of just putting comparing the Fourier coefficients. And then let's take the absolute value of this one and then check. So this implies that I will have a of g epsilon. So this is equal to ag times epsilon 1. They are all real numbers, positive. So I can take here, just write it like this: epsilon 1 to the a1, epsilon 2 to the k2, and so on up to epsilon n to the kn, like this. Yeah, so if at one cusp, I mean ag is 0, then from here we can see that I mean when I transform it, yeah, at the other cusp it is also automatically 0. Okay, so what are the corollaries of this one? So is that, suppose if I have f to be, let f be, and automorphic form. Okay, but not the cusp form. Then so all the KIs have to be the same. Then K1 equals to K2 equals to Kn. So think about this, why this is happening. We can discuss this during the discussion session. So just think about why this is happening. And then the other one is the fact that the other one is this fact. So this is called the Gutsky Queequeg principle. Okay, and so what is it saying? It is saying that if I have if I have f of z equals to summation, g belongs to the dual lattice here, and then ag, and then e to the power of 2 pi I s of gz. Okay, and suppose that this is holomorphic. Okay, and the periodic in on some domain. So we all need those conditions, and then you assume that ag, so it should have this growth on the Fourier coefficients, or minus 8 times a of, so this is more general. Okay, for some constant a. Okay, then ag not equals to 0 implies g bigger than or equal to 0. Yeah, so and for cusp forms, I mean, these things, this bound on the Fourier coefficients are going to be there. So so what it means is that if I'm looking for an Eisenstein series, then we better look at Eisenstein the weight where we have all the all the KIs to be the same, very little weight. And it is enough to look for to test for the criteria for being a cusp form at one cusp. Okay, as so in the case of elliptic modular forms, if I want to call a modular form to be a cusp form, then we have to check the value of f at all the cusps. Okay, and ensure that it vanishes there. But because of this Queequeg principle, I mean, we can say that it's enough to look at one cusp. Okay, so maybe we can talk more about this. Yeah. So this is it. These are the things which I wanted to mention, and I have also talked about Eisenstein series. Now I think, so there is also one more thing which I want to point out, which I think Rupam pointed out, that in the definition of this of the scalar product. Okay, so suppose I have f and g to be Hilbert modular forms of parallel weight. So this k is z to the n, inside z to the n, such that f times g is a cusp form. Okay, then we have the scalar product, and we have scalar product f g. Okay, So even though for our purpose it is sufficient, so usually it is this one. So the measure of the fundamental domain has to be here, yeah, and that is integral over f, and then f of z gz bar, and then I had yi to the power of yeah, so this is yi to the power of so, okay, so y1 to the power of k1 times yn to the power of kn, and then we have this d mu. Yeah, when I have only two copies of the upper half plane, so this is and parallel width, then I have only y1 and y2 here. Okay, this is what we wrote. But to define the scalar product, we can look we can define it without this factor mu of f. But this is what is usually written, and I have also written it so that there is less confusion. And here f is a fundamental domain for gamma, so everything remains the same. And then we looked at so this, okay, so so here is this theorem. So using this, okay, we can show that mk gamma is finite dimensional. Okay, and proof is the same as in the case of elliptic modular forms. Okay, so I have a proof here. So it's a sketch of the proof. Once I have this Peterson inner product, then it's similar. So it's enough to show it for SK. Yeah, so enough to show the complex dimension of SK gamma is less than infinity. Yeah, and for this we pick orthonormal set like this, F1 and so on up to Fm. This is orthonormal. Okay, so with respect to the Peterson inner product norm, okay, orthonormal with respect to the Peterson scalar product. Yeah, so I choose this, and then so in some sense I have, yeah, I mean something like here fi fj, then this is delta ij, the Kronecker delta. Okay, and then you look at, then we consider an arbitrary sum like this, summation say cj fj j running from 1 to m, where the cj's come from C. Okay, and then we now use this comparison of the two norms, which is one of the lemma which I've stated. Okay, then I'm going to use this. So we are going to use, so now use the fact that the infinity norm of f, this is less than or equal to some constant. Okay, so a times the 2 norm of f. So the 2 norm of f comes from the Peterson inner product. Okay, so if I use this, then what I can see from here is that, yeah, so then for every z inside, say h2, okay, we have this sum. Okay, so let's use this in the sum. So we have summation j equals to 1 to m cj fj of z times y1 times y2 to the power of k by 2 here. Okay, and then we'll have this bound. Okay, this is less than or equal to 8 times. I'm doing it only for 2 copies of the upper half plane. Okay, then j equals to 1 to m cj square, and then I take the square root of this. Yeah, so once I have this, then here, yeah, so I can take whatever number I want here, because I'm taking yeah, so I have the freedom to choose the cj here, the linear combination which I'm taking here. Now you take here, instead of cj, the complex conjugate of fj here, and take cj to be equal to fj of z bar. Okay, then I'll have here summation j equals to 1 to n. I'll have the norm of this fj of z, and we are done. So then I will have a times fj of z. Yeah, so this implies that this sum is less than or equal to the norm of a square. Okay, if I divide out by the sum on the right hand side, and then you take the square and then do everything. Okay, so from here we get okay, so j equals to 1 to m fj of z whole square times y1 y2 to the power of k here. So this is less than a square. Yeah, so this is an inequality which we have to check. I'm sitting here a little bit, I'm not showing everything here. Okay, so so now, so if I integrate over f, okay, so then what do we, but the situation is exactly the same as in the case of elliptic modular forms. Yeah, so now if I integrate over the full fundamental domain f, right, then I will show that this m, yeah, this m here, the number of fj's. Okay, then I'll show that you get that m is less than or equal to this constant square times the volume of this is the volume of f. Okay, volume of f. Yeah, so whatever f I take here, yeah, so then that has to be less than or equal to I mean, it's going to be bounded, so it shows that this is finite dimensional. The set of orthonormal sets, I mean orthonormal vectors with respect to the equidistant inner product, it's going to be bounded above. Okay, so this is it, and before I do cusp forms, I want to display one Eisenstein series which is slightly different, and then this is this Eisenstein series is due to Ziegel. Okay, and it's nice to display this. So this is one more example. So definition of so this is due to Ziegel. Okay, so and so he referred to this as the Hecke Eisenstein series. Okay, it's slightly different from the one that we have written, but this also turns out to be an automorphic form. So again, here I start with k bigger than 2, even. Okay, then you define this one. So so Eisenstein series of weight k, okay, and so this is going to be associated to okay, weight k, and so you and b, and okay, a fractional ideal b, okay, inside okay, by g k b of z. Okay, so here the norm of uh, so this b, okay, the Gotek b. So this is another fractional ideal of b that represents b in the class group. Okay, so and this is going to be independent of the choice of this b. So that's, and then this is the restricted sum over what? Sum over all those pairs CD, which belongs to B cross B. Okay, but we take it's up to modulo the units of OK. Of OK, and then again here the same thing, norm of CZ plus D to the power of minus K. Yeah, so we need to show. So this is called the Hecke Eisenstein series, and then yeah, so it differs from the usual one that we have written. It's because of this fractional ideal B, which is appearing. And then what is good about this is the following. So the first thing is that to note is that here, okay, this needs proof. So G K B Z does not depend on the choice of B. Okay, so this B is a fractional ideal of F that represents B in the class group. Okay, and then so this needs proof. GKB. I'm just stating this as facts. Converges uniformly in every those cusp sectors or Ziegler domains. Okay, and then yeah, so we can easily check the automorphic condition for GKB. Yeah, and that GKB, so this belongs to Hilbert modular form. Okay, so here I have here gamma k. Okay, so now what is this good for? What does it do? Then one can check the following. So if I look at GKB and then I look at its value at the cusp infinity, then all we have to do is the limit of as y1, y2 goes to infinity. Yeah, so these y1, y2 are parts of Z. Yeah, so Z is going to be inside H2, and then I'm going to take Z inside this cusp sector, okay, of this GKB Z. Okay, and then one can use the uniform convergence. Okay, and then I will get from here that this is nothing but norm of B to the minus K times this norm of D to the minus K, and then this D belongs to yeah, and this will give me summation D, which is inside B mod. Again, I'm writing here F k star OK star times the norm of dB inverse to the power of k. Yeah, but this is something. Okay, so this is the way we define. This is the zeta function attached to this fractional ideal B inverse. Okay, attached to evaluated at k. Okay, so this is the special thing about this Hecke Eisenstein series. Its value at the cusp, okay, gives me a value, gives me a zeta value. Okay, so i.e. Um, value at cusp infinity uh, of a Hecke Eisenstein series is equal to the value of zeta function. Okay, so it reflects the situation which we saw in the case of elliptic modular forms. Okay, so now uh, so so in fact one can show this. Okay, so this is a theorem due to Ziegler. Yeah, so this is a theorem, and then it says that so GKB of Z. Okay, so the purpose of writing down this is to compare what we saw in the case of elliptic modular forms and then plus 2 pi I raised to the power of 2k divided by k minus 1 factorial whole square and then d to the power of 1/2 minus k times, I will have all those sums coming up. Okay, so this one is sigma k minus 1. Okay, I have the different here appearing, and then b, and then here delta nu. Okay, and then e to the power the trace of this nu z. Okay, and then this sum is over all nu which is inside delta inverse. Okay, and then nu is bigger than or equal to 0. So the trace dual turns out to be this delta. Okay, then so here where this sigma, if I take here maybe sigma, then I want to use some notation here, sigma maybe UA, sigma UA of this, of an ideal. Okay, of this one, delta V. So what should I use here? A, B, C. So maybe C here. No, not C. Maybe B or something here. But B I have already used here. So sigma A of maybe A here of the ideal A. So this is equal to summation the norm of C to the power of U here, where this C belongs to an integral ideal. Okay, belongs to A, and then yeah, so this is integral. So it reflects the U is here. So it reflects whatever we have seen in the case of elliptic modular forms. So this is the good thing. And then what it allows us is that as an application of this, we can show that we can show that these values are these zeta values are integral. Okay, so as an application, one can show. Okay, so as an application, one can show that these values zeta b inverse k, okay, not integral, but so it's so 1 minus k, okay, they are inside rationals. Okay, so what one does is to do this one, we have to look at our one Eisenstein series. Okay, and then what are the properties that we are looking for in this Eisenstein series? We are looking for an Eisenstein series where if I replace the this z coordinate by z. Okay, z1 z2 we had, right? Instead of having z1 z2, I want to replace it by the same, I mean z1 z1. So that's called restriction to the diagonal, and then it is going to give me elliptic modular forms again. Okay, so so let's look at that, how it happens. So this one is Hilbert modular forms. Okay, so maybe on the restriction to the diagonal. So what is the situation which is happening? Diagonal. Okay, so I have f. So let's start with f, which is inside mk gamma k. So this is a Hilbert modular form. Okay, and I'm going to consider then we consider this modular form. Okay, g tau. Okay, which is nothing but f tau comma tau. Okay, so let's make this observation now. Note that SL2Z is embedded, can be embedded inside SL2O. Okay, this is diagonally. Okay, if I have a matrix here, say PQRS, then it is mapped to the same. Okay, PQRS, and then again here PQRS, like this. Okay, so like something like this. It is then my G will have this transformation. Then G has, okay, okay, the transformation, this one, G of say gamma tau. Let's say gamma is this matrix. Okay, then this is equal to, by my definition, it will be f of gamma tau here, gamma tau here, and this is equal to c tau plus d. Okay, now I will have this one c tau plus d repeated 2 times. Okay, so it will, I will have here 2k, one for each of the factors here, right? And then I will have here f of tau like this, and then this is c tau plus d to the power of 2k times g of tau. Yeah, so what does this mean? This means that this means that my g, okay, so this belongs to m2k of maybe SL2Z here, because I'm doing SL2Z here. Okay, so if f has a Fourier expansion, okay, then how does the Fourier expansion of G look like? Okay, so let me write that down. So so let f have this Fourier expansion given by, this is equal to something like a0 plus summation n bigger than or equal to 1, and then delta inverse, okay, and then nu totally positive, and then nu e to the power the trace of here nu z. Okay, so this is the Fourier expansion at infinity. At infinity, then my gz looks like maybe I'll use the notation tau here. Then g of tau again looks like, the same number here, a0 plus n bigger than or equal to 1, and then I will have all these numbers here, indices appearing, delta inverse, strictly positive, and then I'll have here the trace of nu equals to n, and then I'll have here a nu times e to the power of tau here. Okay, so this is the Fourier expansion for G when I have the Fourier expansion for F. Okay, so so what am I having here? So I have here, so again, okay, so this is just a summary. So I have here H, and then this is embedded going to be inside H2. What is the map? I have a tau here, and then this tau is being mapped to tau comma tau here, and then I'll have H2 star mod gamma here, and then over here this will factor through H star, okay, mod here SL to Z. Okay, like this. So my f is a function here. My f is a function here from here to here, and then suppose if this map, okay, is denoted by phi, then this is my G. So first apply phi, and then apply f, okay, and this is my G. Okay, and so if I use this, then what is the restriction of GKB along the diagonal? Okay, so if I restrict GKB along the diagonal, then what one can see is that, so these are some calculations. Okay, so then restriction along the diagonal of GKB. Okay, if I restrict this, then its value at the cusp, okay, will be 1/4. This turns out to be okay. So this is a calculation. It's not obvious at all. So this is zeta of power of 1 minus k. Okay, and then plus on this summation n bigger than or equal to 1, summation like this. This belongs to m to k, and then I'll have here SL to Z. Yeah. So, but now what do we know about these modular forms? This is an elliptic modular form of weight 2k, and then they're spanned by just some Eisenstein series, and then some theta series and things like that. So, and we know that they are rational, right? So therefore 1/4 times zeta of 1 minus k. So this belongs to q. Okay, this is because the divisor sums that they are all integers, okay, as the divisor sums are all integers, and my this one, and m to k of SL2Z has basis, okay, with q coefficients. Okay, so this shows that my this zeta value is actually rational. Okay, so this finishes the sketch of the fact that this is one application of the just the existence of Hilbert modular Eisenstein series. So, for example, one can write this down. I mean, so if I have the time, okay. So, like, yeah. So maybe I will do this during the discussion. This example. Okay. So now, how do I give examples of cusp forms? Okay. So to give examples of cusp forms, we construct what is known as a Hilbert Poincare series. Okay, so okay, so you can refer to this Freitag. Proposition 5.3. Okay, so so the construction is analogous to the construction of an Eisenstein series, and we start with with phi, which is a bounded holomorphic function on Hn. Okay, so on Hn, not on the full Cn. Yeah, otherwise it would have been a constant. So this be bounded holomorphic function, and then so I take and okay, r bigger than or equal to 2, and let's take another complex number w, which is inside Hn. Okay, so then what are we going to do? So I'm going to look at this one. As before, I'm going to look at I want to have a sum which is invariant under the action of gamma. Yeah. So yesterday we looked at so this is what we looked at yesterday. One, okay, with an action, slashing action of m, then so that whenever I apply m again and again, I mean any other n which is inside gamma, yeah, the sum remains the same. So today what we are going to do is that instead of this 1, I take this phi. Okay, and then I take here m inside gamma. Okay, and this is denoted by f r. Okay, so this action has an r, and then with respect to phi. Okay, and this is how we define it of z. Yeah, and but it's not just this one. Okay, so this is the thing. Okay, so here is the definition. So this is summation m inside gamma phi of mz divided by the norm of m times z minus w bar, okay, to the power of 2r times the norm of cz plus d to the power of 2r. Okay, so this Poincare series is also treated in the case of elliptic modular forms. This is also treated in Miyake's book. Miyake. Okay, this is for modular forms. Poincare series. Okay, so so the thing is that this so this is a definition, but it should make sense. Okay, but yeah, so then this converges. It's an analytical result, absolutely. Okay, and in fact, it converges uniformly on compact subsets of h to the n. Okay, so yeah, so since I have this series which converges absolutely and uniformly on complex subsets of Xn, so therefore you can see that this F is holomorphic on h to the n, okay, and it satisfies f of mz equals to n of cz plus d to the 2r times f of z. Okay, everything for all m inside gamma. Okay, but then it turns out that well, this is just a power series which we have defined, and then so we have to show that we have to convince ourselves that this is a class form. So we can set this as a goal for ourselves. Okay, that my f is class form. Okay, so here comes the utility of the Poincare principle. It says that it's enough to look at the cusp at infinity. Okay, and then we directly compute it, and then we show that that has to be equal to 0. Okay, that's some analysis. Okay, by the Kotsky. Principle. Enough to prove at cusp infinity. Okay, so more precisely, we want to check if this happens. The limit as ny goes to infinity of sum of this one. Yeah, so norm of I'll have here mz minus omega bar times n of cz plus d to the power of minus 2r equals to 0. Okay, so it's a little bit involved. I don't think I have we don't have the time to go through this one, but the proof is just complex now. I mean, it's yeah. So let's say this. Okay, so proof. Maybe it's uses. So we have to show that the two things. One is that yeah, maybe I can just leave this proof. Okay, so this is I can refer to, I think, Freitag, this proposition. Freitag, proposition 5.3. Okay, so the first thing to note for the proof is that, that there is a certain symmetry in this sum. Okay, so even if I interchange the z and then the w, the series is not going to change. Okay, so which means that it is enough to take limit as the instead of saying ny goes to infinity, I will take now nw goes to infinity. Yeah, so that will n and then the imaginary part of w instead of taking y. Yeah, here. So that's the thing which one has to observe, and then there are some bounds which one has to establish. But yeah. Yeah, so maybe yeah, so let's see if we can do this in the discussion. But then this is the theorem as a result that this one f of z, I mean Poincare series, f of z, this is a cusp form of weight 2 times r. Okay. Okay, so yeah, I have to so I just have 15 more minutes maybe. So there is a well studied um, um, yeah. So there are Hecke operators on the space of modular forms, and I just want to briefly say what those are. So it's about the Hecke action on Hilbert modular forms. Okay, so for this we look at Hecke operators. Okay, we are going to define Hecke operators as double coset decompositions of certain kinds of matrices, and then the best way to do this is using the adelic description of Hilbert modular forms. But I'll just define what these Hecke operators look like in some special cases. Okay, so so in general, what happens is so we can look at so gamma naught of say n. Okay, so these are going to be the congruent subgroups. Okay, I think I define this as the kernel of SL2O to SL2 of O mod of n like this. Okay, so this is also a discrete subgroup, and for Hilbert modular forms on with this as a discrete subgroup, we can define we can define this for SL2O also. Okay, so this is the gamma k that we had, and what we do is we look at, suppose I have a prime p which doesn't divide n. Okay, this be a prime ideal. All right, then I choose and pi p. Okay, this is a totally positive generator of P. So the right way is to view my pi P as an element of the addels of K, okay, which is one everywhere except at P. Okay, then you look at, okay, I'll give you the reference for this section. Okay, so this TP, so these are going to be defined as these matrices, comma not of n. Okay, and then 1 0 0 pi p times gamma naught of n. So these are 2 by 2 matrices, and it's going to act on my Hilbert modular forms, and it has a coset decomposition like this: gamma naught of n times ui. Okay, I runs over, yeah, some indexing set. Then you define it as, and define f, okay, say of weight k, and then dp. So this is defined to be the sum of summation f k, and then this ui, some indexing set here. Okay, and as in the case of elliptic modular forms, then it preserves the space of cusp forms. Okay, so we need to show all these things, but yeah, so mk maybe of level n, I can just write n here, and then mkn, and then so this preserves yes, space of cusp forms of weight k, okay, and the discrete subgroup gamma naught of n over there. Okay, so it's a little bit in so I forgot to mention, so it's a little bit more involved to define other operators. There are other operators which are okay, so maybe one more operator is okay. Also one can look at this S A for an ideal A, and then again this is going to look like gamma naught of n, okay, and then alpha 0 0 alpha gamma naught of n, okay, where, yeah, so my alpha equals to product of all primes q says that, yeah, so pi q to the power of the valuation, the qwidth valuation of A, like this. So it's a bit more involved, okay. And these are the Hecke operators, and then in the definition of the Hecke operator, the way we have defined it, though the way we have chosen the coset decomposition, it depends upon the choice of ui, but after we define the sum, it is independent. Okay, so these definitions are independent of the choice of the uis and then the uniformizers. Then we create this space, this algebra, okay, which is the okay, which is the Z subalgebra of the endomorphisms of, yeah. So then I can look at the endomorphisms of Sk, okay, and then here n, and then this has the this contains the this TPs, SA, and things like that. Yeah, and then the algebra was generated by these Hecke operators. It's known as the Hecke algebra. Okay, so algebra generated is called Hecke algebra. Okay, and it's many times denoted by T0 of n here. Yeah. Then one has a good theory of new forms and all forms. Okay, here also. So there is a good theory of new forms and all forms here. Okay, but to be able to do this, we have to first define the concept of an eigenform of a Hecke algebra. Okay, so what is it? So this is, maybe I can put a star here. So T node of n. So this is a fact. So this is commutative. This is a commutative algebra. Okay, and it comes with an inner product on skn. Okay, so and so that allows us to diagonalize same reason as we have in the case of elliptic modular forms. Okay, is so I have a finite dimensional space sk, and on that sk I have a commuting family of operators. Yeah, so I'm saying that all of them are diagonalizable and admits common basis of eigenvectors. Okay, and these eigenvectors are the eigenforms. Okay, and these are the eigenforms of all the Hecke operators. Okay, and then there is this very famous theorem of Shimura. What can I say about the eigenvalues of a normalized eigenform? Normalized means when I make the first Fourier non-zero Fourier coefficient to be equal to 1. Okay, I just divide out by whatever occurs as the in the Q expansion. Okay, and then I just divide out by that one. Okay, so there is a way to do that, and this theorem Shimura. This is also from this 1978 Duke paper. Okay. So if I have F to be FB normalized eigenform, okay, but with one condition. Okay, with all is a condition on the weight with all ki of the same parity. Okay, of the same parity. I mean, either all of them are odd or all of them are even. Then the Fourier coefficients are algebraic numbers. Then the Fourier coefficients of F are algebraic numbers. Okay, algebraic numbers. They are in Q bar. Okay, and Okay, so the field which is obtained by adjoining all the Fourier coefficients, okay, is also a number field, and field K subscript F obtained by adjoining all the Fourier coefficients of F is a number field. Yeah. So in the same paper, you can okay. So, but the idea to show that it's that the Fourier coefficients are algebraic numbers is the same as we have in the case of elliptic modular forms. Yeah. So that's because we know that. And the way we have defined the Hecke operators, there will be algebraic relations between, like, TP and TP square. TPQ is TP times TQ, and yeah, using those things and the fact that it is normalized eigenform, we can conclude it's more or less the same. It's not so different. Okay, yeah, so in the same paper you can find a counterexample why you need this the Ki of the same parity. Okay, so that's a nice counterexample that it's not true in the case when you don't have this what you call the component weights here. Okay, Ki's when they have different parity by using some Hecke characters. He gives an argument why we cannot expect it to be algebraic numbers. Okay, so so yeah, so once I have this Hecke eigenforms, then there is this theorem. This theorem due to many people. Okay, this is Blasius, Rogowski, okay, and then Taylor. Yeah. So it says that suppose if I have F over Q to be totally real, and I have K equals to K1, Kn, okay, okay, and F belong to Sk of n. Suppose this is an eigenform, Bn eigenform of the Hecke operators d of n. Yeah, and suppose I denote by OF to be the number field, to be the ring of integers of the number field Kf. Okay, so OF is the ring of integers of Kf. Okay, so so then once I have an eigenform, then yeah, then totally real and be an eigenform of them and OF. Okay, so this is the Hecke ring. Okay, okay, so maybe I can erase this. Okay, eigenform of Tn such that I have this such that there exists a morphism theta f from Tn to OF. Okay, so what does this theta f do? So theta f is the map which takes this TP to the pth Fourier coefficient. Okay, so it's going to look like f evaluated at t is equal to something like theta f of t times f. Okay, and when I apply it to TP then or TL for any prime L not dividing n, then I'm going to get here the Elliott Fourier coefficient of f, exactly the same as in the case of elliptic modular forms. Okay, then what we can get is that we can get a representation of the Galois group. Then if lambda is a prime of OF, there exists a continuous representation. There's a continuous representation from where to where. Okay, rho f from the Galois group of f bar over f, okay, to GL2 of this number field OF, but completed at this prime lambda. Okay, and it is going to have similar properties as we have seen in the case of elliptic modular forms, like which is unramified outside, unramified outside the n times the norm of lambda. Okay, so it is like this, and we know, and this from the determinant of this representation, yeah, we can get the weight of f also. Okay, so this is this theorem is similar to or a generalization of the existence of Galois representations for Hecke eigenforms, Hecke eigenforms, yeah, in the case when we have SL2Z over Q. Yeah, so yeah, so maybe with this I'll stop.
So, thank you, Chandrakant. Are there any questions? So, Chandrakant, this Shimura's result, it says only algebraic numbers. Huh? It doesn't say algebraic integers.
Yeah, it doesn't say algebraic integers, but one can refine this.
Maybe some bounded denominators kind of thing, right? Or
yeah, so one can refine this actually. So it's in this yeah, it only says algebraic numbers, the result as it is. You're talking about the Fourier coefficients, right?
Yeah.
Are you talking about the Fourier coefficients?
Yeah. I'm talking about the.
Oh, okay. So so maybe this is known, so I can just write this down. So that so this is by Shimura. So so that this if I adjoin to Q the values of the Fourier coefficients of f, then this is totally real or imaginary. Okay, but this totally real or imaginary, but this imaginary is of a totally real field. Yeah. So this is also similar to what we have in the case of we have in the case of elliptic modular forms. I think this is, yeah, this one is proposition 2.8. Proposition 2.8. Yeah. And for the algebraic integers, we have that in this situation, in the, which is called the parallel weight case, parallel weight case, um, the eigenvalues values are algebraic integers.
I see. Okay. Thank you.
Yeah, yeah. Yeah.
And I have a general question.
Yeah.
Like, what are the things that you especially get for Hilbert modular forms that you may not get for automorphic forms? Are there probably some?
Oh, for Hilbert modular forms which are not automorphic.
Yeah. Is there?
I mean, for a general automorphic form.
Yeah.
Yeah. So I guess there can be automorphic forms which are not Hilbert modular. I mean, there are things which are defined over the symplectic groups and so on.
Okay. Okay.
So I think it's just a matter of terminology.
I see.
Yeah. But the treatment which we have given, which is especially in this also the book by Freitag and then van der Geer, is that they do everything once and for all. But in this in the book by Shimura, this book, the arithmeticity of automorphic forms, he does it everything at one go for all GLN and things like that. Here we are doing only with GL2R to the N and then subgroups of that, right? So I think it's possible to give a general treatment. I don't know.
So for the beginners, you recommend Freitag's book or what did you? Yeah.
Yeah. So so this book by Freitag, I think it's Freitag, Freitag, Hilbert modular forms. So this is kind of readable, although I have heard that it has some mistakes here and there, but I haven't found maybe. And then the other one is this volume on modular forms. It's called 1 to 3 of modular forms. 1 to 3 of.
Oh yeah, you mentioned that.
Yeah, of modular forms.
Okay.
But if we can read Freitag, I mean, then I guess this is what, if I remember correctly, this is what Professor Ghate also made me read when I was about to give a talk, and that was a long time ago. It benefited me a lot. And then the third one is this paper by Shimura. And this is this 1978 Duke paper.
Okay.
Yeah, so the disadvantage of Freitag is that he doesn't define Hecke operators. I mean, he has written the book for a very, special, to prove something. So he doesn't define what Hecke operators are. And it's also, but Shimura does it, I mean, everything so well. Yeah.
Yes.
It's very detailed in Shimura.
Yeah.
I think this is also the 1 point, Shimura's paper is also the 1 point reference for many other papers.
Okay, thank you.
Yeah. So are we meeting at 4?
Yeah, we are meeting at 4.
Okay.